Any question about the homework or the lecture? Okay. If you don't have any question, please download the discussion handout. Okay. So here's our some summary. This week we learned about what is minimal sufficient statistic. And this is definition. And there are two main theories. So we usually use these two theories to check whether this is minimal or not. So especially the first one. The first one is we have to find the ratio of the density and figure out when if it's not depend on theta. If this ratio is not depend on theta, we have to check if this is the minimum statistic and the statistic is the same. Yeah. Okay. And also there is a very helpful theory is a exponential family. So if you can show that the distribution is an exponential family, then we can find that this statistic Tx is sufficient and is also minimal sufficient. Okay. But you have to check that the domain theta contain an open set. So usually you have to check full rank. Yeah. Full rank can imply the meta space contain the open set. Okay. Okay, and also we have a definition of the ancillary statistic and the complete statistic. Okay. And yeah, we can also use the exponential family to check the completeness. So I forgot to ask. So if x1 to Sn, there are ID full rank exponential family, then we may have the text is complete. Okay. Okay. Any questions so far? Can T be anything? No. The T can only be this one. So if you want to use a series of exponential family, we can only say this T is complete and sufficient. This T. Okay. Yeah, but you can also use some property of like so if T is minimum sufficient, and G is a one-to-one function, then G of T is also minimum sufficient. Yeah. To transfer C to another function, okay. What has to be a full range of what frequency to cut? Okay. Do you mean this one?
Yeah. Like what are you saying has to be full rank? What is the full rank? What does that mean, full rank?
Okay. So okay. So in here, this eta is a function of theta. So eta is a function of theta. Theta is our parametric space. So maybe I should this theta, and it may contain to some function. Okay. Let me see how to I explain this. A way to do that is we have to derive it over theta and check its form rank. So if this is RK to RK, then what we can do is we can do the partial derivative over eta. This is a function of theta. So this is is k times k matrix. So if this is full rank, then we say the exponential family is full rank.
So the derivative of the Jacobian of eta basically has to be full rank.
Yes. Yes, Albert, you're right. So when we can say yes, yes, but how do we define the four dimensionality? The way we define four dimensionality is using the derivative of the over eta. Yeah, it's use this metric to define the four dimensionality. Yeah.
If that's not full rank though, I thought another way of checking the condition was if you can find like k linearly independent whatever.
Oh yeah. You mean yeah? That's also correct. Yeah.
So
So
it doesn't have to be full rank, but if it's full rank, then it's true.
yes, you're right. And you can find like the find like a eta theta 1 to eta theta k, and this one is a linear independent. Okay. So if the eta is a function to RK, you can also find this.
Will eta always be a function from uh, rk to rk? Will it always like will the parameter space always have the same dimension as the um, the range of eta?
Yeah, it's not always, but if this one is larger than originally case space, then it cannot be full rank.
Okay.
Yes. Like the example, the Albert set is a mu and f of mu. In this case, not full rank. Yeah. Yeah, that's a great question. Yeah. Okay. Any more questions? Okay. So if you don't have a question, let's go to the discussion problem. Okay. The first one is minimum sufficient. Okay. Okay, I think the order is not good. Let's do 1 and 4, which is about the minimum sufficient. Statistic, okay. Let's do 1 and 4 first. And let's look at a question. Okay, so we have this is exponential theta theta. Okay. And you want to first you want to find the minimum sufficient for theta. And the second one is you also have to show the whether it's compute or not. Okay. So in A, you have to use these two theory. You have to choose one. Usually, both series can hold, but sometimes they may have the one which is easier. Yeah. Use these two. Choose one. Okay. And B, you just check the definition. Okay. Yeah. The 4 also is a minimum sufficient. But I see this one is easier. You don't have to apply theory. Yeah, you still have to use a theory. Okay. So please do 1 and 4. And if you have any question, don't hesitate to ask me. I just realized I did something wrong. Sorry. So if the primary space contain open same, this is a this is full rank. Okay. And another sufficient condition for this T is a minimal sufficient is that you can find theta 1 to theta k, and you check the theta 1. This is linear independent. Okay. And the follower can make sure this is happen. Can make sure you can find you can find k point also and the theta needle such that this is linear independent. Okay. Yes. So this full rank, and you need the if you need the completeness, you have to make sure this is full rank. So yeah, sorry about that. Yeah. Okay. So I think the other one is also 13. Full rank. Yeah. Okay, let's go through the question 1 and 2. 1 and 4. So in question 1, we have this exponential family, this exponential distribution. So S1 to Sn, they will follow exponential theta theta. Okay. And product from I to N. We want to check is minima sufficient. So first step we check is a sufficient statistic. So we find the density. Okay, so it's density is theta inverse. Si greater than theta. Okay. And this is equal to theta to the negative power n exponential negative summation si divided by theta. How about I write it like this? Okay. And this term is equal to indicator the smallest one greater than theta. So we have this. Yes, minus n is right. Okay. And you can think that this is a function of this one and this one. So we can use the factorized theory. We can show that the is sufficient. Oh yes, person. Yeah, sorry. Thank you. It's person. Okay, so this is sufficient. Okay. And then we want to prove that it's minimum sufficient. Here I want to use what's the number theory? I want to use this one. Okay. So 6.2.30. Okay. Okay. So I want to find a ratio of the density. So given not equal to y, the ratio of density this can be the exponential theta summation si minus summation yi And we have the indicator S1 greater than theta. Indicator Y1 greater than theta. Okay. Okay. So the first thing, if this one equal to this one, and S1 equal to Y1, then the ratio okay. But we have to put a lot of weight. So if uh but this one is much harder, so we can use we can do the thing like this. We can make assume it's not equal to this. Then you can think that the function is obviously depend on theta. Yeah. The ratio is depend on theta. Okay. So by the theory, 6.2.30. This is minimal sufficient for theta. Okay. So your question is if this is sufficient. Okay. So you can think like if this one is equal to this one, then this term is equal to 1. Okay. Oh, okay. Order statistic. Okay. Okay, let me think. Does the order statistic is sufficient? That's correct. But why when is minimal sufficient? Yes, that's correct. Yeah, the order statistic is minimal sufficient. Eh? let me think. Lots of the dependence on the theta.
I don't think it's minimal sufficient. I think it's sufficient, but
Okay.
you you can have the ratio not depend on theta without the order statistics being equal.
Okay. The ratio is depend on theta.
And so it's not.
Oh yeah, yeah. You're right. Yeah. So
It's sufficient, but not minimal sufficient.
okay, how do I use this to see that? So if the order statistics are all the same, there is independence correct. But if they are,
I mean, another way to say it is just the order statistics is not a function of the sum.
yes,
So it's not minimal. I mean, we just showed that the sum is, yeah, exactly.
yeah, it's not one-to-one function, so it cannot be minimal sufficient. Yeah, thank you. Okay, yeah, thank you guys. And so this is first part, and the second part is complete statistic. Complete or not? Okay. So if usually this type of question, they want us to show that it's not complete. Yeah. Okay. So the way to do that is you find non-trivial ancillary statistic. Okay. So one way to do that is like this. So I found 1 to n. The average of this one is well, the average of this one is okay. It's n theta. Yes, because divided by n, so ratio is 1. So yeah, it's n theta. Okay. And also the S1, oh, sorry, this minus theta. Because Si minus theta is exponential theta. Okay. And also S1, the minimum one needs follow exponential little theta is n theta over n. Yes. Okay. So the mean of this is equal to theta over n. So that's imply the mean of the smallest one is equal to 1 plus theta. And this implies that the is equal to 2n theta. Okay. So that means we can find a linear combination of these two statistics and which the expectation is 0. So like this. So we can say Si minus 2n x1. This is equal to 0 for all theta. Okay. But this is not okay, so we can say this is a function of g summation si s1. Okay. But g is not 0. Okay. So this is not compute statistic for theta. Okay.
So are we trying to find a function of the statistic that's first order ancillary? In other words, the expected value doesn't depend on theta?
Yes.
Okay.
So the definition of completeness is every function g is this means is auxiliary.
Isn't that first order ancillary?
Sorry. Yes, the first order. Yeah, sorry, first order. Yeah, first order. Yeah, because we only find the first moment, so it's the first order. Yeah, you're right. Yeah. Okay.
Also, could you explain again how you found that the distribution of the order statistic is exponential? X.
Do you mean this one?
Yeah.
Okay, this is property of exponential. So the way we do that is we just so if s1 to sn are exponential theta, then the probability of s1 smallest one greater than t is equal to probability of si greater than t to the power n.
I see. Okay.
Yeah, then we plug in a density of exponential, then we can find that. Yeah.
Okay.
Okay. Any questions? Okay, so the question 4. Okay. Okay, the question 4. Okay. Yeah, the question 4 is similar. So we just find the short is minimal, so we have to use a theory. Okay, so the density is, look at this. Is equal to the only thing you have to be careful is the z is a parameter. So here we have two parameters. One is theta, another one is z. So we have to write the formula like this. Pull down 2 sigma square xi square and indicate z equal to 1. And the product theta over 1 exponential, sorry, 2 theta. Indicate the function z equal to 2. Okay. So in the end, you may have some function of the theta and z. And we have another, you have indicated exponential summation si square multiply this indicator function z equal to 1 and indicator function z equal to 2. Okay. Okay. So again, by the factorized theory, this 2 is a severe statistic. And you can also find the ratio of statistic density to show that this is also a minimal solution. So, okay. So we use the same procedure. Yeah. That's 1A. Okay. So now the rest of question is about the complete statistic. Okay, so don't know whether we have. Okay, now I give 5 minutes to look at the question, and I will show you how to do that after that.
Could you post the solutions to these problems on Canvas?
Yes, I will write down a solution. Yeah. Okay, so
Could you also post the solutions from last week's discussion?
I see I did. You can
Oh, you
find
did.
a solution in the canvas. Yeah,
Maybe you did. Sorry, I don't know if I checked.
that's fine. Yes, I will run down the solution question. Yeah. Okay. Okay. Uh, the cylinder is not if and only if. So we can only say if it's full rank, then it's complete, but we cannot say it's not full rank, so it's not complete. Yeah.
But I mean, so we have this theorem that says that if the x's are IID full rank exponential, then T is complete.
Yes.
Therefore, like, so if A then B then is equivalent to not B implies not A. So if T is not complete implies that the x's are not IID full rank exponential family.
Oh, okay. Yes. But actually, the question one is not exponential family.
Yeah, I guess
Yeah,
so.
yeah,
It just
yeah,
looks a bit like that, but I guess the thing dividing, like the theta that is dividing in the exponent, like I guess
yeah,
that
yeah, yeah. You are right. Yeah.
doesn't fit.
So if it's not complete, so you can say it's not full rank. Yeah. Okay, let's go to question 2 and 3. Okay. Question 2 is okay. This is this one is a discrete variable, and question 3 is a continuous. Okay. And usually, if you want to show the completeness of a discrete variable, you always do the same thing. Yeah. With plugging the variable and see and see what happens. Yeah. So we have to make sure that if this g of x is depend on some parameter, this is theta. Okay. For theta, then we have to show that g is equal to 0. Okay. So this is what we have to do. Okay. So now this is equal to, okay, summation theta from 0, x from 0 to minus theta n. Okay. Okay. And we have the g of x, and the density is, sorry. Okay. The density is theta choose x. Theta choose x, n minus n, theta choose n minus x, right? N minus theta, okay. And the denominator is n choose n. Okay. And we have some condition on the, I think it's not a matter. Okay. So the way we do that is like this is a function of theta. So this is a function of theta. So we can say we like the edge of needle, which is equal to g of needle and theta choose needle. So theta is needle. So needle choose needle and n choose n. And sorry, this, yeah, this n minus a. Okay. So this should be little. So that can imply that the G of little. It's not an exponential over theta or x. Expectation over x. So with summation x, theta is the unknown parameter. Okay. Okay. So we have this.
Why are you plugging 0 into G? So can you explain just H? What is H of 0? I'm not quite
Okay.
sure.
So I define this function as h of theta. So now I find theta equal to 0. So like the minimum 0 n summation x equal to 0 g of x 0 x n minus x n minus n. So because of this, so x can only be 0. Okay. So we have the g of 0 0 0 n n n n. Okay. And this can imply that g of 0 is 0. Okay. Okay. Does that make sense? Yeah.
Yeah, thank you.
Yeah. Then we have to do another. We have to do h1. So which is equal to s equal to 0 to 1 g of x and 1 choose x and choose n minus x and choose n. It's because g of 0 is 0, so we only have, we can plug in is equal to 1. And yes, so that can imply g1 is 0. So we have the g1, 1 choose 1, n choose n minus 1. And it can, this is 0. That can imply g of 1 is 0. Okay. And so on. And in the end, we can show that all the gi is 0. So it's complete. Okay. Yes. So usually if you will deal with the discrete continuous decrease variable, we have to plug in the theta. Yeah. Okay. Next question. Okay. On this one. So for A, we want to show that if x divided by y is independent to y, yes, then this is equal to this. Okay. This one is you can we can do the thing like this. Exponential Sn is equal to and this is equal to a binary independent. Good. Okay. So we show this equation. And the interested part is question B. Okay. Here we want to use the Basu theory. Okay. To show that if there are gamma distribution, alpha is known, then this Then we have this. Okay. This state is trivial. Okay. So we just multiply t and divided by t. And the next day they translate this like this. This is, so if the small si, these are independent to t, then this t is equal to it's independent t, so okay, this can equal to t, and if these two are independent, and this is equal to, and by a, this one a. Okay. So we only have to show that these two are independent. Okay. So okay. So we have, what we have to do is the shown t is complete, and si divided by t is, then we can apply the Basu theory. Okay. Okay. So t is summation si alpha 1 to summation xj j from 1 to I. See. Okay. So this is follow the gamma distribution. I alpha beta. Okay. Yes, I alpha beta. Okay. And we can use the density. So the density of T is so the density of T is equal to I alpha beta I alpha T to the power I alpha minus 1 and exponential negative divided by beta. Okay. Okay. The only unknown parameter is beta. So here we can apply, theory. Distribution. Then we can show this is exponential distribution. So, and the beta is absolutely the full rank. So T is complete. Okay. And another part is we have to show this in theory. Okay. Si, the smallest, the F order statistic. Okay, how about this? S1, S2, Sn, now gamma, alpha, beta. S1 divided by beta, Sn divided beta. Now gamma, alpha 1. So if this is divide y1, y2, yn, then Si, this is equal to Si divided by beta and t divided by beta. This is equal to yi divided by summation yj z from 1 to I. Okay. And this one is independent to beta. So Si divided by y, t is ancillary statistic. So we can apply theorem, Basu theorem. Okay. Okay. So usually when you deal with continuous relativity, first step you check whether it is a exponential family or not. So if it is exponential family, then you will be lucky. But if not, if it's not exponential distribution, then I suggest you to do that. You find this and define the function as the h as a theta, and you find the derivative of theta. Okay. So the derivative of theta should be 0. Then you can find some relationship, and in the end, you may be able to show that it's complete. Okay. So okay. Okay. So I think that's today's discussion. And if you have any question, feel free to let me know. How do I stop recording?